Okay, hi everyone. My name is Brian Skinner. I'm at Ohio State University, and today I want to share with you my March meeting talk from the 2020 March meeting about the universal plateau and the thermoelectric Hall conductivity of Dirac and Weyl semimetals. So I'm a theorist. This is work I did in part with theory colleagues, Vlad Kozy, who's now at Berkeley, and Liang Fu, who's at MIT. But the real star of this show is actually the experimental work that I'll talk about, which was done by collaboration between two groups, the group of Xiaosong Wu at Peking University, and in particular his student Wenqi Zhang, and the group of Li Wanzhang at the Southern University of Science and Technology in Shenzhen, and in particular his postdoc Peipei Wang. Okay, so this talks about the thermoelectric effect, and maybe just to remind you, the thermoelectric effect is when you apply a temperature gradient across a material and you see a voltage gradient arising. And the way to understand it is that when you heat up one side of a material, the hot carriers tend to have a higher diffusion constant than the cold carriers, so they tend to diffuse away from the hot side and accumulate on the cold side. And as a result, you get a voltage difference associated with charge carriers accumulating on one side. And the strength of this effect is quantified by the so-called thermal power, or Seebeck coefficient, which is the ratio of delta V to delta T. Now, in a good metal, we usually define the thermal power using the Mott formula, which tells you how to calculate the thermal power if you know the conductivity and its dependence on energy. So in particular, you're seeing the thermal power depends on the derivative of the conductivity d sigma dE, basically because the conductivity tells you about the diffusion of carriers, and you need a difference in diffusion for higher energy carriers in order to get the effect. But in this talk, I want to move beyond the normal Mott formula for good metals. And for that, I'm going to need to look at a more generic definition of the thermal power. So you can define the thermal power S in terms of a generic response when a system has both electric current and temperature gradient. So here you're seeing the electric field that you observe, and the heat current that you get depends on the electric current that you apply and the temperature gradient that you apply through a combination of tensors that are described by this matrix. So this, for example, resistivity relates the electric current to electric field. The thermal conductivity kappa relates the temperature gradient to the heat current, and these off-diagonal components are the thermoelectric conduct, or the thermal power, that relates, say, the temperature gradient to the electric field, as I mentioned above. But there's also this Onsager relation between the top right component and the bottom left component. And basically, you can also define the thermal power in terms of the heat current that you get for a given electric current. So in particular, now there are two equivalent ways to define thermal power. You can either think that when no electric current is flowing, the thermal power is delta V over delta T, or when the temperature is uniform and you do have electric current flowing, the thermal power can be defined as the ratio of a heat current to electric current. And this is actually the second definition is the one that's going to be more convenient for me to use for most of this talk. That large thermal power is when a given electric current gives you a large heat current. So the thermal power, of course, is a very useful effect. It's basically a way to convert waste heat into useful electric power. So the way you make these devices, practically speaking, is you make a junction between two different materials, one that's N-type, meaning heat and electric current is carried by electrons, one P-type, carried by holes. And now you make a junction between them so that when heat comes in, the heat flows in parallel down these two legs, but the electric current goes in series. And this allows you to extract useful work. You can also run the effect in reverse. So instead of putting a load resistor here, you put a battery that forces the current to go through the circuit and thereby can carry heat away from something that you want to cool. And these two equivalent definitions of the thermal power basically guarantee that any material that has a large thermal power can be used for either purpose with equal effectiveness. Okay, so what you actually do when you make a practical device, you chain many of these little junctions together in series, and now you can use that either for heat recovery or for refrigeration. Unfortunately, in a practical sense, the thermoelectric effect is usually limited to very niche applications. So, using it as a cheap thermometer, or just for characterization of a material, its carrier type, or for something where you absolutely need to have no moving parts that need to be serviced like a human being, like you want something to work on a satellite or something like that. And the reason why this effect is sort of too inefficient for large-scale applications, why you don't have a solid-state refrigerator, you have something with lots of moving parts, can be understood by looking at the efficiency of a thermoelectric cycle. So in particular, imagine that you make a junction between N-type and P-type material, you put some load resistance, you allow yourself to tune the load resistance to get optimal efficiency. What you'll find is that the efficiency of your cycle depends only on a particular dimensionless combination of numbers that we refer to as the figure of merit. Usually written as Z times T, ZT. So the figure of merit depends on the thermal power squared, basically because any electric power you extract depends on voltage squared, which comes down to thermal power squared. It's linearly proportional to temperature T because you need your carriers to carry a lot of heat current, and the heat current they have is proportional to temperature. It's inverse to electrical resistivity because you want any power you generate to not be lost as Joule heating inside your material. And it's inverse to thermal conductivity because if you have a high thermal conductivity, then you'll be unable to maintain a large temperature difference across your sample. So in particular, if you do the calculation, you'll find that the device efficiency, the efficiency of your thermoelectric cycle, looks like TH minus TC over TH. This is the usual Carnot efficiency, which is the upper limit for any thermodynamic process, multiplied by some dimensionless function f of a dimensionless number ZT. In particular, it looks like this function, which turns out to be very slow. So in particular, if ZT is, say, 2, then your f is still only about 1/10. So there really is a lot of room to improve ZT and to really make a big difference in the effectiveness of thermoelectric devices. Okay, so before I tell you how to make a good thermoelectric, let me first talk about how to make a bad thermoelectric. And metals are bad thermoelectrics. So here I've just rewritten this figure of merit ZT, taken this definition, and instead of writing resistivity, I've written thermal conductivity, it's inverse, and I factored out some factors of kV over E. And in this formulation, you see two dimensionless objects. So there's the thermal power in terms of its natural unit kV over E, and then you see this combination sigma T over kappa. And you might recognize this combination because in a good metal or any Fermi liquid, this ratio is just an order 1 number, so 3 over pi squared. This is the Wiedemann-Franz law. So the reason then that metals have such bad thermoelectric efficiency is because S is small, the thermal power is small. And the reason, the quick way to see that is that the thermal power looks like the ratio of heat current to electric current. And in some sense, all the electrons carry electric current, but only a very small fraction carry heat current. So when the metal has some finite temperature, there are some excitations near the Fermi surface. So all the heat current is basically confined to some narrow window kBT around E Fermi, whereas all these electrons are carrying heat current. So when you do the calculation, you find that the thermal power is of order kBT over E Fermi. So in a good metal where E Fermi is the equivalent of 10,000 Kelvin, this CT is some impossibly small number, and you'll never make a useful device out of a metal. So for that reason, all the useful thermoelectrics are semiconductors, where you can play the game of moving the Fermi energy just by changing how much you dope the material. So now let's imagine playing the game of going to different doping in a semiconductor. If you dope your semiconductor very heavily, then it will have a large Fermi energy and basically act like a good metal, and figure of merit will be small. Now, if you reduce the Fermi energy just by adding fewer electrons, eventually you'll get to a point where kBT is bigger than E Fermi, and now your electrons sort of look like a thermal gas or a Boltzmann gas of charges. And the electric current basically looks like some drift velocity times the total number of charges, N times E. But the heat current, each electron has sort of kBT of heat. So the heat current looks like kBT times the number of electrons times that same drift velocity. So when you make the ratio, you find that the thermal power is of order kV over E, and consequently ZT is of order 1. Now, I should say that I'm actually being very optimistic here because I assumed that there's no additional contribution to the thermal conductivity coming from phonons or something. And actually, in lightly doped semiconductors, usually this Wiedemann-Franz law is strongly violated. And this object here, sigma T over kappa, is usually a small number instead of an order 1 number. Now, if you move the chemical potential even lower, you dope even more lightly, then you find that your system goes through a metal insulator transition, becomes an insulator, chemical potential falls into the gap, conductivity sigma is exponentially small, and ZT is very small. So the point is that as you play the game of imagining moving the Fermi energy around in a semiconductor, you'll find that the maximum ZT you can imagine is some order 1 number. So for this reason, progress in thermoelectrics has been very slow. So here you're looking at the maximum reported ZT for different classes of materials over the last 60 years, since 1960. And you see that it improved from a world record of 0.5 to maybe 2.5 in 60 years. And so for those of us in solid state physics who are used to Moore's law, this is a very unpleasant situation. So the idea of this talk is to look at the Dirac and Weyl semimetals. These don't obviously fall into either description, metals or semiconductors. They're like metals in the sense that there's no gap between, there's no band gap, but they're like semiconductors in that in their undoped state, they have vanishing density of states and there's no Fermi surface to talk about. So the question is whether these things can do something for thermoelectrics that our conventional metals and insulators cannot do. Okay, and of course, at this point, there's a whole industry of identifying 3D Dirac and Weyl semimetals. I won't go through this. There's been amazing and fast progress in the last decade. But I'm going to focus in particular on this one, zirconium telluride. Okay, so when you first start looking at the thermal power of semimetals, it seems like this is all a bad idea. And the reason is that the virtue of a semimetal is supposed to be that you can have electrons and holes coexisting simultaneously. But if you have electrons and holes simultaneously, then you'll find that they tend to cancel in the thermal power. So just imagine running an electric current, then holes will move in one direction, electrons will move in the opposite direction. And in doing so, they will cancel in the heat current. They're carrying heat current in opposite directions, even as they carry electric current in the same direction due to their opposite charge. And so that will give you a small thermal power. And the way to think about this in terms of moving the Fermi energy is that when the Fermi energy is very big, your system looks like a metal. It has thermal power kBT over E Fermi. But then when you bring the thermal power down, when you bring the Fermi energy down, so the Fermi energy is smaller than kBT, then you start to excite holes in the valence band. And those holes cancel the electrons in terms of their thermoelectric, their thermal power. And so as you come back down towards zero, the thermal power goes back to zero and reaches a maximum of order 1 or kB over E. So if you want to make something useful in the thermoelectric sense out of a semi-metal, you need to find a way to make electrons and holes contribute additively to the thermal power instead of canceling. And the big idea is to do it by putting material in a strong magnetic field. So in particular, imagine you have some material that has electrons and holes simultaneously, and you put it in a very strong magnetic field. If the field is strong enough, then you'll find that the electric field tends to point mostly perpendicular to the direction of current flow. We say that you tend to have a large Hall angle. Now, in this situation, you have electrons and holes that are moving in crossed electric and magnetic fields. So the magnetic field is going out of the plane. The electric field is sort of, say, in the X direction in this picture. And in this situation, you can just think back to what was your favorite class in E&M, and remember that in crossed electric and magnetic fields, charges move by the E cross B drift. And what's important is that the E cross B drift goes in the same direction, regardless of the sign of the charge. So electrons here might do clockwise spirals and holes do counterclockwise spirals, but they drift in the same direction, which is the direction of E cross B. So now if you look at the thermal power, the ratio between heat and electric current, the electric current looks like some drift velocity, or this E cross B drift velocity, times the number of holes minus the number of electrons, because now they're canceling in the electric current because they have opposite charges. But they're adding in the heat current. So in particular, if charge flows mostly perpendicular to electric field, then you can describe this as a reversible process. And the thermodynamics of reversible processes says that the heat current is related to the entropy current, Js here, which means it looks like some T times the same drift velocity times the total entropy of electrons plus the total entropy of holes. So finally, you get this really nice formula that says that the thermal power is just the total entropy divided by the net charge in this limit of large Hall angle. So now what you can do at this point is just make a calculation of the thermodynamic entropy in a Dirac or Weyl semimetal as a function of magnetic field. So what you're seeing here in this calculation is that at small magnetic field, your thermal power just looks like some T over E Fermi. As you turn up the magnetic field, you start to have well-formed Landau levels, and you get oscillations in the density of states, and therefore in the entropy associated with these Landau levels. Then finally, at sufficiently large magnetic field, you enter what's called the extreme quantum limit, where only one Landau level is occupied. And as you turn up the magnetic field, the density of states associated with that Landau level is proportional to the magnetic field. Basically, the density of states is proportional to the number of flux quanta in your system, and that goes up as you turn up the magnetic field. And so the entropy in your system is going up, kBT over E, excuse me. Then finally, when your magnetic field is large enough that basically only the lowest zeroth Landau level is occupied, you reach a situation where kBT becomes bigger than E Fermi, and now you have a population of thermally excited electrons and holes all dwelling in the lowest Landau level. And that's possible because I have this gapless spectrum that has an electron-hole symmetric lowest Landau level. So as I turn up the magnetic field higher and higher, density of states of that Landau level gets higher and higher, which means I start to get a thermal gas of electrons and holes. I have ever more entropy as I turn up the field higher and higher because I have more particles. And the important thing is that these electrons and holes contribute additively to the thermal power, and that allows the thermal power to keep rising and rising without saturation as a function of magnetic field. And just to show you that this is unique to the Dirac spectrum, if you do the same thing in a conventional semiconductor, you see a similar sort of small thermal power, some wiggles. It starts to go up as you enter the extreme quantum limit, and then finally saturates at some order 1 number, some order kB/E number, when kBT becomes bigger than the Fermi energy. And this non-saturation really comes down to, really is because you have an electron-hole symmetric lowest Landau level that allows you to have electrons and holes simultaneously, and very many of them that all contribute additively to the thermal power. Okay, so experimentally we wanted to test this physics, and we decided to look at the Dirac material zirconium telluride. Zirconium telluride is a great material because it has a single Dirac cone with a very small gap, if there's a gap at all. Actually, this material lies at the boundary between being a topological insulator and a trivial insulator. So the bulk bands are almost touching, and you have a sort of linear dispersion. And it's sort of unclear whether there is a gap, but experiments seem to agree that if there is a gap, it's very small, less than 10 millivolts. What's nice for our purposes is that it has a very low carrier density, maybe 5 times 10 to the 16. So it's very easy to reach this regime of extreme quantum limit where only 1 Landau level is occupied. And it has a very high mobility, nearly 1,000,000 centimeters squared per volt second. So it's easy to reach the limit of large Hall angle. Okay, so when you measure the transport, what you see is you see rho xx here. And what you're seeing, these little wiggles in rho xx, are the Shubenkopf to Haas oscillations that indicate the presence of well-formed Landau levels. And actually, because the mobility is so high in this thing, you start to see Shubenkopf to Haas already at about 1/10 of a Tesla. And by 1 to 2 Tesla, you're already in the extreme quantum limit where you have only 1 Landau level occupied. Okay, so I'm not an experimentalist, but the experimental setup goes mostly like this. You have a heater and a heat sink, and you suspend your zirconium telluride crystal. It's a 3D bulk crystal, sort of millimeters in size. And you have a thermocouple measuring the temperature on the hot end, and then you have various voltage probes that allow you to access both the Seebeck coefficient, the SXX, normal thermal power, as well as SXY, the Nernst coefficient. And then you have voltage probes also allowing you to read off the resistivity rho XX and rho XY. So an actual picture of the device looks something like this. Okay, so our theory prediction is basically that this thermal power should rise linearly in B in the extreme quantum limit with a slope that depends linearly on temperature. So, okay, so here's the data at low temperature, and what you're seeing is something that maybe looks linear in B, and the slope keeps increasing with temperature. It looks pretty good. If I just take this theory curve and I put it on top of this plot, it looks something like this at 40 Kelvin, which is okay, pretty good. And the problem, of course, is that I'm not showing you. And if I unhide this, what you start to see is that at higher temperature, this slope, instead of continuing to increase with temperature, saturates. And it gets even worse if you go to high enough temperature. Instead of a really sharp slope with magnetic field, you see something that even reverses sign and goes to some plateau. So that by the time you're above 100 Kelvin or so, the thermal power has switched sign, which usually is the sign of the thermal power just tells you whether the heat current is being carried by electrons and holes. Electrons or holes, and somehow that's switching here. So the reason is that in zirconium telluride, it's sort of known that you have an evolution of the carrier number as a function of temperature. So what you're seeing here are APS spectra, and at a low temperature, you're seeing the Fermi energy residing in the conduction band. And as you turn the temperature up, the Fermi energy starts to drift down into the valence band. And so you have something that goes from being N-type to something that becomes P-type. And the explanation for this is that in addition to the Dirac cone, which exists at the gamma point, you have at some other point in momentum space a sort of heavy electron band. And its heaviness means that you essentially don't see it in transport quantities, that any electron drift velocities are very small, but it has a relatively large density of states. So when you turn up the temperature, you can easily thermally excite carriers away from the Dirac cone and into this heavy band. And so as you turn up the temperature, this heavy band sucks more and more electrons away from the Dirac cone, and you see the carrier number going from N to P. You can also, just by measuring the Hall, the Hall effect, slope of rho xy tells you the sign of the carriers, and you see this evolving as well, not just as a function of D, of B, but also not just as a function of temperature, but also as a function of B, that somehow the magnetic field also changes the density of states associated with this other band. So the carrier concentration evolves as a function of both T and B. So this whole situation is kind of messy. If, we had this simple prediction, and now this evolution of the carrier concentration is making things complicated. So we decided to see if we could find something simpler to look at. And basically our inspiration was to think about the normal quantum Hall effect. So in the normal quantum Hall effect, rho xx is extremely complicated, has lots of wiggles and bumps, and there's a whole zoo of interesting physics hiding in here. And sigma xy, on the other hand, is kind of simple. It has a series of plateaus. So the thermal power of Seebeck coefficient is kind of like rho xx in the sense that it looks like a longitudinal voltage. So it might be simpler to look at something that looks like a transverse conductivity. And in particular, you can talk about the thermoelectric Hall conductivity alpha, and specifically the thermoelectric Hall conductivity, the transverse part, which now will look like the heat current, say in the y direction, divided by the electric field in the x direction. So this is JQY over EX. So there's actually a simple relationship between this thermoelectric conductivity alpha and the thermal power. They're basically, you just multiply by the resistivity tensor and you get the thermal power. Okay, so how do you think about this thermoelectric conductivity? Well, let me first talk about the familiar picture of 2D edge states in the quantum Hall system. So in the quantum Hall system, we know that we have these sort of Landau levels, and at the edge of the sample, those Landau levels sort of bend up in energy. So this is sort of position in the sample, and when you get to the edge, the Landau levels start to come upward in energy. Right at the edge of the sample, you have electron states that either move into the page or out of the page. This slope looks like a dk dE or dE dk that sort of tells you velocity, and you have opposite velocities on this side versus this side. On one side you have edge states going in, the other side you have edge states coming out. Okay, so imagine measuring the thermoelectric Hall coefficient, which looks like the heat current divided by the electric field. When I have no electric field, you say, okay, on one side I have sort of thermally excited electron hole pairs on these edge states that are carrying heat into the board. On the other side, I have those same excitations carrying heat out of the board, and I have no heat current. When I make a bias, what I do is essentially I just shift these, I shift the chemical potential up or down on either side, but I have the same heat current on the right and versus the left. Here I have two edge states carrying heat, and here I have, on the left, I have two edge states carrying heat. And so my net heat current looks like 0, and my alpha xy is 0 when the chemical potential is in the middle of two bulk Landau levels. On the other hand, if I move the chemical potential so that it's sort of intersecting a Landau level, then on one side I have two edge states carrying heat, say, into the page, and on the other side I have only one edge state carrying heat out. So when I make this ratio of the heat current divided by the electric field, it looks like something of order E over H. So consequently, I can say that alpha xy looks like E over H times the number of Landau levels that I'm intersecting, which is either 1 or 0 in the 2D case. Now in 3D, our situation is pretty similar, except that in a Dirac or Weyl semimetal, you have this 0th Landau level that sort of partly disperses up and partly disperses down when it hits the edge, and I have no gap between the electron and the hole type Landau levels. So you can think that, okay, I just have a sort of picture like this, and because I have a 3D system, I have a picture for every z momentum. So I should sort of integrate over every possible value of the z momentum. Another way you can say it is that in 3D, Landau levels don't just look like discrete energies. You have the momentum in the z direction as well. So electrons in a given Landau level can have a range of z momenta. And we often describe this by saying that the spherical Fermi surface has now been discretized into a series of cylinders. and the electrons, filled electron states, live on the surface of these cylinders. And as I turn up the magnetic field, the spacing between the cylinders moves outward. So the quantized values of kx squared plus ky squared become more densely spaced. But the point is that I always have a certain number of Landau levels intersecting the Fermi, intersecting the chemical potential. But I have fewer and fewer of them as I turn up the magnetic field. So if you do the calculation for 3D, you find that alpha xy looks like the same E over H. Because it's three-dimensional conductivity, you need a momentum scale. That momentum scale looks like T over V Fermi. In other words, this is the typical change in momentum associated with thermal excitation times the number of bulk Landau levels intersecting the chemical potential. So in 2D, that number was sort of 1 or 0, depending on whether I put the chemical potential in the middle, in a gap, or in the middle of a Landau level. But in 3D, this number can be large when the field is large. Okay, so if you do the calculation of alpha xy using this edge state picture, what you find is something that at small magnetic field, meaning many Landau levels are occupied, I have something that depends on the electron concentration and on the magnetic field. This number here is basically the number of occupied Landau levels. But when I turn up the field large enough that only one Landau level is occupied, I get this really nice result that says that alpha xy now just looks like some integer that is the degeneracy of the Dirac point. Basically, how many states I have per z momentum in the lowest Landau level. In other words, this integer here has sort of gone to 1, or whatever is the degeneracy of the Dirac point. So what's nice about this thing is that it essentially depends only on universal constants and the Fermi velocity and some integer. So in that sense, it sort of looks quantized. I shouldn't call it quantized because there's no topological invariant or anything that's protecting it. But what's happening is that the thermoelectric Hall conductivity has become independent of the strength of the magnetic field. It's become independent of disorder. It's become independent of the electron concentration, how many electrons I have per unit volume. And amazingly, it's become even independent of whether my carriers are n-type or p-type. So within the lowest Landau level, I can shift around the carrier concentration, even move it from the electron type to hole type. And I'll find that alpha xy doesn't change at all. And that's going to be important for zirconium telluride. Okay, just to show you a theory calculation, this blue curve is what you get if you set tau to infinity. Basically, you say there's no scattering, no dissipation of any kind. And you'll see that alpha xy comes down, there's some wiggles, and finally it settles at this universal plateau. If you include the effect of finite disorder scattering, you'll basically find that this alpha xy first turns on as a function of b. Basically, when you have small omega c tau, it's this Hall response very slowly turns on. And then when you reach omega c tau greater than 1, it follows the same dissipationless calculation and eventually settles at the same quantized plateau. And just to contrast this with the usual semiconductor situation where you have a p-squared dispersion, you get no such plateau. There's no universal behavior at large B. Okay, so experimentally what's done is that you make 4 separate measurements. You measure the transverse and longitudinal resistivity, rho xx and rho xy, and the transverse and longitudinal thermal power, Sxx and Sxy, or in other words, the Seebeck coefficient and the Nernst coefficient. And you can extract alpha xy by making this combination of them. So let me just remind you that the resistivity and the thermal power are both separately complicated objects. So the resistivity has complicated magnetoresistance effects, and it has this, rho xy has this weird behavior associated with changing the carrier type from n-type to p-type as a function of temperature and magnetic field. And similar problems plague Sxx, or Seebeck coefficient, as I talked about, and Sxy is complicated as well. But when you make this combination of them, you see something very nice, which looks like this. So here's the thermoelectric Hall conductivity alpha xy, and what you're seeing is that at large magnetic field, it saturates into this plateau that's the same that doesn't change as a function of magnetic field or as a function of temperature. So alpha xy over t has no dependence on temperature. And I should emphasize that the different curves in this plateau really have very different carrier type, carrier concentration, but they all come to the same value. And this value agrees pretty well with theory. There's unfortunately a kind of large uncertainty in the theory prediction because the Dirac velocity is not known with very high precision. But within the precision of the numbers we have available, it's really a very good agreement with what we predicted for the plateau. And because alpha xy now has acquired a dependence only on Fermi velocity, this in principle becomes a thermal probe now for, 1, whether you have a Dirac-Weyl dispersion, and 2, you can measure the Fermi velocity. And as you move the field around, you could now map out what the Fermi velocity is as a function of the field direction, because the only thing that matters in the extreme quantum limit is the Fermi velocity in the field direction. Okay, so that's pretty much what I have. Just to remind you, I talked to you about some theory work, both for the idea of large thermal power increased by magnetic field in Dirac and Weyl semimetals, and then the theory behind why this alpha xy acquires the universal plateau at large B. And I showed you that at least in the Dirac material zirconium telluride, these experiments, these predictions seem to be borne out quite well by experiment. And I'll point you in particular to this just published experimental work in Nature Communications. And thank you for your attention.